This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Morning, everyone. So this week will be busy week, right? A lot of mid-semester exams. So what do you think about this subject? Most of cases we have to deal with integrals. It's a subject of integrals. From Fourier series representations to Fourier transform, Laplace transform, we have to deal with integers all the time. No. Not integral, what I'm talking about. So that's why you probably need a prerequisite of engineering mathematics. But this subject is very useful subject. You probably have noticed this subject is prerequisite for many subjects in electrical engineering. I think it's also a prerequisite for some subjects in mechanical engineering, mechatronics as well. So from this week, we started to talk about, there's no battery here. Okay, so we start to talk about the Laplace transform. As I mentioned, engineers really love Fourier transform. It gives you a frequency components of signals. However, mathematicians really like Laplace transform because Laplace transform will teach you how to find solutions of differential equations using Laplace transform. Let's revisit what is Laplace transform. You see same thing many times, again, and again. So it will take a while to log into system. So let me just try to write down. Okay. If you have a signal, xt, can you see this one clearly? It's probably not the best way of doing it. If I have my signal xt, okay, t, its real number is normally positive. I shouldn't write down this one. I can see this one. My t belongs to R. And my xt is also belong to R. Okay. I need to check condition 1, 2, 3 so that I can write down my x omega. It will be minus infinity to infinity xt e minus j omega t dt. So this is Fourier transform. So do you still remember what are three conditions? I put 3 ticks there. What are 3 conditions? Okay. So basically you need from minus infinity to infinity absolute value of my xt is less than infinity. And you also need any finite interval, you will have finite number of these continuous points, and also you will have many finite number of minima as well as maxima. So this is the 3 conditions which, if you limited everything in one period for a periodic signal, it will be same 3 conditions for Fourier transform. Okay. So we know that in order to check these conditions, my UT, a step signal, does not satisfy this. Any periodic signal will not satisfy this either. So that's why we introduce concept of generalized Fourier transform. And you also have to remember my omega is a real number. If my Fourier transform exists for this signal, this x omega is a continuous function with respect to this omega. And if you have a generalized Fourier transform, this continuity of this x omega will not be there. Okay. So let's look at if we keep this. And let's look at something about Laplace transform. So what Laplace transform is doing is my same thing is my x as it will be. I only consider signal from 0 to infinity. So I'm doing same signal and e minus st dt. So now same, my x t is a real number. My x s is a complex number, and my s is a complex number. So the differences is the s and omega. So you can see if my s, I can write down my real part plus imaginary part. I have to make sure if my sigma equal to 0, that indicates that this one will be exactly same as my Fourier transform. And when you completely ignore signal from minus infinity to 0, right? Okay, so in this case, I have to, because as I mentioned, I'm still dealing with an integral, which is an improper because this part can be infinity. I still have to make sure that the integral from 0 to infinity, everything here should be smaller than infinity so that this improper integral is well defined. Okay, so in order to do that, we will call something is a region of convergence of x. So this one, because you can always play with this sigma, so that, for example, if this sigma is positive, you will have damping term of original signal, and adding damping this signal, because you have exponential damping if my sigma is positive. And that's why by playing with sigma, you can always have a region that for some region where I define my sigma, this integral, and in a proper integral is well defined. And in order to make sure that, okay, my x and substitute s by g omega equal to my x omega, that indicates my sigma equal to 0. So my sigma equal to 0 if within the domain of convergence, that indicate I substitute s by g omega, I can get Fourier transform. So this is the results it was saying, because you can see I substitute s by 0 plus omega, it will become a Fourier transform. And sigma is 0. I have to make sure this point must be in the region of convergence of this signal. That's how everything should be explained. Okay. That's kind of revisit of what we are talking about. This is this results, and this is explanation. Because if this one is outside the region of convergence, basically you can't substitute this sigma to be 0 to get my Fourier transform. Okay. All right. So today I want to give more examples of my Laplace transform, and I want to be slow so that you can get this concept very clear. And this concept will be very useful whenever you want to deal with the systems. So we first talked about if you have exponential function, decaying function, e power of bt uk, and for some b belong to R. I highlight this one. Why? Because when I was talking about Fourier transform, I have to require this b must be a positive number, so that the integral from minus infinity to infinity of this signal take absolute value will be less than infinity. However, when I'm talking about Laplace transform, it's not necessary, because Laplace transform of any signal exists provided you define the region of convergence. So we talk about the region of convergence is always my real part of my x is larger or equal to minus b. And if b is positive, and my origin or 0 will be inside the region of x, which you can see if b is positive, you can always easily find my Fourier transform of signal. So it just substitutes s by g omega. Okay. So we also talk about transformations. These properties of my Laplace transformations. These properties are very, very similar to Fourier transform. Because if you take s by with g omega, if the Fourier transform is well defined, you can recover almost everything. Okay. However, I highlight last lecture, I hope you still remember, the most important thing is the region of convergence. I hope I highlight enough times so that you will pay enough attention, and I believe those kind of concepts will appear in your exams. Not for the middle semester. Okay. So when I'm talking about the linear one, okay. So what I was talking about, if I have x 1t, I will write down my x1s, and I have my region of convergence x1, and x2t, I will have my x2s, I have region of convergence x2. And if I apply the linearity, I will consider this a x1t plus b x2t, it will be a x1s plus b x2s, and I will have the overlap of the region of convergence, so that everything is well defined. In this overlapped region, both Laplace transform of two signals exist. So when you consider time scaling, that's also easy. So that's something when I'm talking about this kind of time scaling, xt, and I will consider my region of convergence x, xs, and my xat, you will have my 1 over a x. Okay? So I can consider s of a will be my s prime. Okay? So this s prime must belong to region of convergence of x. So that also indicates my s should be a region of convergence of my x. So all the tricky parts for the Laplace transform go to the region of convergence. Is that making sense? So when you are doing this, you have to pay attention. And why I want to highlight, because I watched a lot of YouTube videos, a lot of references for Laplace transforms, and not many people talked about these important things. You can see all these properties, they write down it as what we can see right now without thinking about the region of convergence, because the situation will be very complicated if you write down precisely. People just assume that you understand the concept of region of convergence and then you can use it. So I highlight these modulations and I will do this one right now, trying to see how this could work. Okay, so I will do first one, and I will show one example to tell you how to use the induction to find the case for any integer capital N. So let's look at this case. When n equal to 1, I need to show is my t, x, t corresponding to, Alright. So when capital N equals to 1, I need to show that t xt Laplace transform is minus n capital N equal to 1 is my d, ds, my xs. Okay, so how should I prove it? Okay, I want proof is my 0 to t, 0 to infinity, my t, xt, e minus st dt. This is by its definition. Can you see this? Okay, so, okay, if I want to take derivative of whole thing with respect to s, how should I do? I assume that my t is independent of my s. So I can swap the order of integral and the derivative. So I can write down this part. Okay. So what's this value? Okay, that's probably not correct. So if I just ignore this t first, consider original signal, and I will take this value, df. So I will consider original signal, take the xt Laplace transform, and take a derivative with respect to s. And because xt is irrelevant, so that part will be 0 to infinity xt. Now, if you take derivative of e power of st with respect to s, I will have minus t e minus st dt. Okay, so this one I can take minus out, and I will get t xt. So I can get minus 1, 0 to infinity, t, write down next step. I can write down is minus 1, 0 to infinity, t, xt, e minus st dt. This is Laplace transform of my t xt. So this is basically shows that if I'm doing Laplace transform of this one, it's just the derivative of my xs with respect to s. So how should you do the induction? You can always assume that when capital N equals to k, this relationship holds. And then from that one, I will prove when capital N equals to k plus 1, the same relationship will hold. I will show this one from example of the one of the questions. I couldn't remember which one here. So it's the first question of chapter 7. So it's question 81. All right. So this is how everything should prove if you consider something related to any capital N. So this is question 81. So let me first to prove first question, 81A. Okay, here is t, e minus bt. I want to show Laplace transform is s plus b. Okay. All right, I will provide two different methods to show how this can be proved. Okay. First one is always by its definition. So what I'm doing is I'm trying to consider, sorry, did I miss ut here? Yes. Okay, so I will have 0 to infinity, t, b minus t, And ut is always 1 for 0 to infinity, and then I have minus st. Okay. So that's easy. I have to write down this part t and e minus b plus st and dt. I will use integral by parts. Okay. And I will consider this t is my first variable, and my du dt will be constant 1. And I will consider my e minus b plus st will be my second variable. I will consider my v dot t will be e minus b plus st, and my vt should be, take the integral, will have minus b plus and e b plus st. Maybe I should change to this one as well, so that both of you can see clearly. We all can see clearly from this side, this side. Is that better? Okay. Now, when I'm doing integral by part, this one will equal to u and v. So I will have my t and minus b plus s e minus b plus s t. My t value will be 0 at t equal to infinity. And then I need to minus this du and vt. So you basically use this part and this part again. And because vt have minus sign, and I minus, and with minus sign, I will have at integral from 0 infinity b plus s e minus b plus s t. So I'm trying to be slow, and sometimes when I'm writing things, I think what I wrote is not consistent with what I thought. So you probably help me to check any error when I'm writing down things. So if it's this case, I can always putting them together. So it will be my minus b plus st e minus b plus st, and t equal to 0 and infinity. And this part, I will have b plus s 0 to infinity e minus b plus s t dt. So again, I will have the same thing here, not changing. And I will have b plus s, I will have another b plus s, this square, and because this is minus, I will have e b plus s. So all I need to know, okay, when t equal to 0, everything will substitute, this part will be 0. And same here. So what I need to consider for this case is I need to figure out limit t goes to infinity e minus b plus s and t. So if I can find this limit, I can find the solution easily. And what's this limit? My s, again, I can write down sigma plus j omega. Okay, I don't care about j omega because e j omega t minus j omega or positive j omega take the absolute value. Amplitude is always 1 because real part is related to cosine omega, imaginary part is related to sine omega. So what I'm trying to see is if I will have limit t goes to infinity, e minus p plus sigma t. So I don't have to worry about second one. All I need to do this. And if my b plus sigma is positive, and as t goes to infinity, this part will decay to 0. Okay, so in this case, if my b plus sigma is positive, my first term, take t equal to 0, my t term will be 0. And take second term, t equal to take first term, t equal to infinity, it will be another 0. So this part will completely disappear, because when t equal to 0, this one will be 0. When t equal to infinity, this part will be 0. And now, if you consider this case, when t equal to infinity, this term will be 0. It's negative term. And when t equal to 0, this term will be 1. And negative will be positive. So it will be b plus s squared. And, okay, so my region of convergence of my x1 t will be E t minus. It will be my s belong to R, belong to C. My real part of my s should larger than minus b. Okay. So this is very standard way of doing it. And I was trying to do the second part, use same thing. I found very difficult to prove, so that I will provide a second method. Okay. So the method, still t, e minus bt, and ut. And I call this one is my x1t, okay? And I will take derivative of my x1t. What my derivative of my x1t? I will have first consider this t. It will be 1, and I keep e minus bt. And because I take everything from 0 to infinity current stage, I completely ignore the role of my ut. Okay, so I will have this part. I will also have, when I take derivative, I need to consider fix this term, take derivative of first part. Then fix the first part, take the derivative of second part. This one would be minus b and e minus bt. Okay? And this one will be e minus bt plus minus b t minus e minus bt. Am I correct? Because I'm saying is the signal I'm caring about from 0 to infinity. Because I'm doing Laplace transform, right? So Laplace transform only cares about everything from 0 to infinity. So from 0 to infinity, I don't care. Because ut is always 1 in that region. Okay. All right. And I also know that when I consider my x0, 1, so you can see my u t 0 minus will be 0. So in this case, this part will be 0. And I also want to highlight this one is minus b x1t. Okay, now I want to use the properties of derivative signal trying to do simple things. Okay? And if I realize, okay, what I'm having here is my x1 dot t equal to e minus bt minus b x1t. Okay? Both sides, I will take Laplace transform. They will should be equal, right? So if I'm taking Laplace transform of my left-hand side, it will be my x s minus x1 0 minus. Am I correct? And then this side, I know this one pretty well, is s plus b 1. And then I will have b. Now I'm using the linear properties of Laplace transform, and this one will be my x1s. And this part is 0 because my step signal at 0 minus will be 0. So in that case, I can put these two x's together. I will have s plus b. I will shift this part this side. xs equal to s plus b. And my x1s will be which one is simpler? Okay. Sorry? Of course, it should. There are many different ways of doing the same thing. You can use different properties, of course. Yeah. But this one is very useful if I want to solve the equation 81, question B. Okay? So, if I'm doing this one, I want to show for any capital N, which capital N is an integer larger or equal to 1, this relationship holds. And I want to show by mathematical induction. So how to do the mathematical induction? This probably I want to spend some time to explain, is I always have to choose for the first value, capital N equals to 1, this relationship holds. And I already proved that in my step A. Then, for the mathematical induction, I will assume N equal to K, this relationship holds. And I have to prove when my N, sorry, I have to prove when N equal to N plus K, capital N equals to K plus 1, the same relationship holds. Okay? So the step 1 is already finished from the 81.8. So we just show that. And now, so let me assume so when I'm doing when N equal to K plus 1, okay? So what I'm doing is my T, K plus 1, E, B, T, and U, T. So that's why I provide the second method. So I will again call this one is my x1 is always changing. I'm call this one is my x1t. And I will take derivative of my x1t. And again, as I explained earlier, I completely ignore ut because my Laplace transform considered from 0 to infinity. So in this case, take derivative of first term, we'll have k plus 1 here. And this one is t k e minus b t. Right? Now, I have considered keep the first term and take the second term derivative with respect to t. I will have plus t k plus 1. This one second term derivative is minus b, e minus b t. Okay. And this part will be k plus 1, t k e minus b t plus minus b, and this one is my x1 t. I will do Laplace transform for both sides. So I also know my x1 0 minus, it will be 0 because my step signal at t goes to 0 minus will be 0. So if I'm doing this Laplace transform, I will have my s, x1s minus x1 0. This part is k plus 1 is constant, and we use the assumption of induction, which is I will substitute Laplace transform for capital N equal to k. This one will be my k s plus b, k plus 1, and then this part will be b, x1 s. And this part 0. And I will shift this part back, and I will have s plus b, x1 s, and s plus b, k plus 1, this part. Am I correct? Then if you divided this s plus b back, you prove everything. And if you do by integral by part, it will take a long time to find this. But if you do this way, it's much simpler. Okay. Any question? Any question? Okay. So as I mentioned, for this one, we use mathematical induction to do this one. You have to consider when capital N is equal to 1, we just prove it, and then you assume capital N equal to K, you assume this relationship holds, and then you have to prove when capital N equals K plus 1, the relationship still holds for N, capital N equal to K plus 1. Okay. So then let me talk about integral. Integral will be quite tricky. I want to prove that one as well. So the integral of this t of my x lambda d lambda, and I call this one again x1t. I just use x1t like an internal variable, trying to make things easy. And I have to know my x1 t 0. This part is 0 because when you consider this t, substitute from t minus, everything here will be 0. Okay, when I'm taking derivative, it will be my x And now I have to go back again to think about my properties of my derivative. So if I'm doing Laplace transform for both sides, I will have s my x1s minus x1 and because this term is 0, so my x1s will be question. Why I need to highlight this derivative property a lot? Because we want to solve the differential equations. Everything you think about is linear combinations of derivative. And you can see, if I'm going back, consider examples in very early chapters. If you look at this example, equation 1.33, I can take Laplace transform for both sides. Then I can get a relationship between my input signal x and output signal y. So that's what this relationship you will encounter is transfer function. It's also related to something we call the impulse response. So you can see, if I deal with this case, I can easily get my system in Laplace domain. Because if this equation 1.33 represents a physical system that's characterized by ordinary differential equation and also its linear time invariant, then if you take Laplace transform for both sides, you can get the relationship between my input signal xt and output signal yt. And that's why it's important to solve this differential equation use Laplace transform, and you don't have to worry if my transformation exists for signals. Because people might consider why we can't use my Fourier transform. As last week talked about, when you are doing frequency response for a system, you have to assume my system must be stable, which also indicates my impulse response absolute value taking from minus infinity to infinity should be less than infinity. That also indicates the impulse response will go to 0 as t goes to infinity. That's very strong assumption, and I told you a few physical systems do not satisfy this condition. So that's why Laplace transform is important. It didn't care about what conditions for the signal. As long as you play with the domain of the convergence, everything will be fine. Okay, so that's the important things is for any system, any signals, you will have Laplace transform. You probably don't have Fourier transform. You will have transfer function. You probably don't have the frequency response. Okay. So we mentioned this part, and here it's the same thing when I'm consider TUT. It's the same thing. You can always consider doing the same thing. You can consider my x-axis is 1 over square s squared. And similarly, you can always consider my ramp signal. It will be an integral of my step signal. You can always use my integral properties of this part. So how should I do that one? In a simpler way. Okay. So you know my t, ut. I take derivative of this signal will be my ut. Okay. So you can do two different ways. So if I'm doing this part, I will consider x1t, and my Laplace transform of my ut, you should remember this one, it's very important. For the Laplace transform, for important signals, you have to remember impulse is constant 1, and step is 1 over s. So if I'm doing this part, and I know x1t equal to 0 minus is 0 because I'm dealing with step signal, and then I will consider my x1 dot is my ut, and I will take Laplace transform both sides. This one will be s x1 s minus 0 equal to 1 over s. My xs is so this is a similar thing, but you don't have to go through the definition. And for this signal, you don't have to worry. You know that this signal does not have Fourier transform. Definitely, my s equal to 0 is not in the region of convergence. Okay. And we showed this one already in the first question of chapter 7. We just showed this one, so I don't have to do this. Okay, that's probably end of my part, and from next week, Jamie will start to talk about inverse Laplace transform, Z transform, inverse Z transform, as well as my transfer function in continuous time domain and my transfer function in the discrete time domain. And you also have to learn, okay, what's a state space representation. So you have to always remember Laplace transform is important. It can get information of the system. So any system, you can find the transfer function from Laplace transform directly from ordinary differential equation. Then you can always consider my output signal in the S domain will be my input signal multiply my transfer function. And if you want to get every signal back in time domain, you have to take inverse Laplace transform to get my output signal in time domain. So instead of using convolution, you will use multiplication of two functions in the S domain and doing inverse Laplace transform. Okay. So I probably see you tomorrow for the mid-semester exam. It was booked for 1 hour and a half. You will have 50 minutes of reading time. You can finish roughly about 1 hour, and you can leave early because they can't book the time just for 1 hour. That's what they require. So it's 1 hour exam. I don't think it's very difficult, but I don't know.
Tried to do it like several times, but I can't get to this one, the final answer. I get something else, and I don't know how to come from here to here.
Okay.
I just want to see where I was wrong.
So first, let me just make my things organized. I'm totally if you are doing this part.
This is the integral, and I try to divide it in 2 parts.
Yeah.
Because it's even, we can forget the imaginary part, we have only the real part, and I just go to steps, and I don't know how to get to this one. I tried to look it in the internet, but I also couldn't find it.
So you have this part, right?
Yeah.
And this one is